let us discuss the concept of the derivative. As you remember, we discussed the problem of finding the slope of the tangent line to the graph of the function. And the approach we took, we started out by trying to find the slope of the tangent line at point x, of this green tangent line. And the way we looked for the slope of tangent line is by using the second lines. So we step away some distance h away from x. If h is negative, then it will be to the left. So we find this point x plus h, look up to the graph, and we find the point on the graph of the height f of x plus h. So now we have 2 points, one with coordinates x and f of x, another with coordinates x plus h and f of x plus h. So we can form the formula for the slope, and this is exactly this difference quotient. And then we let h go to 0 and figure out the limit. As h goes to 0, this point on the left approaches x. And so this red second line becomes more and more like the tangent line. Once we find this limit, then we will get the slope of tangent line. We also discussed the problem of instantaneous velocity, or the problem of finding the velocity function for some object. So, briefly, if we have this function s of t, which is a position function, s of t is the position function of some object, then we can calculate the instantaneous velocity as the limit of average velocities over shorter and shorter periods of time. This fraction represents the average velocity of an object for h units of time, say for h seconds. And if we take limit as h goes to 0, we'll find the instantaneous velocity. Mathematically, this is the same calculation as the slope of the tangent line to the graph. So, putting those two concepts together, in mathematics we define derivative of function f to be f prime being the limit as h goes to 0 of difference quotient f of x plus h minus f of x over h. In practical situations, it is either the slope of the tangent line or the instantaneous velocity, or more generally, the rate of change of some quantity represented by f. Let's prove some of the simple shortcuts to derivatives. Let's start with a proof that derivative of a constant is equal to 0. As the usual proof, we set the new function f of x being equal to some constant. Then to find the derivative, we will need to do the difference quotient. So we calculate that f of x plus h is equal to constant as well. So constant function does not change. Then we set up the derivative as the limit as h approaches 0 of the difference quotient f of x plus h minus f of x divided by h. In our case, both of those function values are constants, c minus c. And since those are two identical numbers, they will cancel each other. So we get limit as h goes to 0 of 0 divided by h, and that is flat 0, just as was promised by the shortcut. In a similar fashion, we can prove that derivative of x is equal to 1. So we set up a function f of x equals x. Then for the difference quotient, we're going to need f of x plus h. That's x plus h. And now, to the calculation of the derivative, for the calculation we set up the limit as h goes to 0 of f of x plus h minus f of x over h. That works out to be x plus h minus x divided by h. To simplify, we remove all the parentheses and we'll get x plus h minus x. Here x and minus x will cancel out. And we have the limit as h goes to 0 of h over h. Both of those h's could be cancelled. And we get the limit as h goes to 0 of 1. And that limit is equal to 1. Let's work on some examples of calculation of the derivative. Let's take function f of x equals x squared and find the derivative of this function. The setup of the problem is you set up the limit as h goes to 0 of the difference quotient f of x plus h minus f of x divided by h. In this case, if we put x plus h instead of x into the function, we'll get x plus h, all of that squared, minus x squared in numerator. After we expand what x plus h squared is, we'll get x squared plus 2xh plus h squared. Then we note that the first x squared cancels with the last x squared, and then we get a simpler expression, limit as h goes to 0 of 2xh plus h squared. Then we see that both of the terms have the common factor h, and we can factor it out, so that we get a limit as h goes to 0 of h times 2x plus h over h. Now we see that h could be cancelled both in numerator and denominator. Then the limit becomes the limit as h goes to 0 of 2x plus h. And into this expression we can put h equals 0 and get the limit to x. In short form, we usually state that derivative of x squared is equal to x, or d over dx of x squared is 2x. Now we can discuss the proof of the following shortcut, that the derivative of the sum of two functions is equal to derivative of first plus derivative of the second. So we set up a function s of x being equal to f of x plus g of x, and we will work on finding the derivative of this function. So we're gonna need s of x plus h, that's f of x plus h plus g of x plus h. So to set up the derivative of s, we make the limit as h goes to 0 of s at x plus h minus s at x over h, which by the above calculation is the limit as h goes to 0 of f of x plus h plus g of x plus h. All of that subtracted the sum of f of x and g of x. We remove all the parentheses and distribute this negative on the second parenthesis and get f of x plus h plus g of x plus h minus f of x minus g of x in the numerator. Now we will rearrange the terms. We'll combine the f of x plus h and minus f of x term together, and g of x plus h minus g of x term together as well. So we get this new fraction. For the next step, we're gonna split that into sum of the two fractions, like that. First fraction is f of x plus h minus f of x over h, plus another fraction, g of x plus h minus g of x divided by h. That's the deal. And then we split that into two limits. Limit of the first fraction plus the limit of the second fraction. And this is exactly the limit of the difference quotient for f and the limit of the difference quotient for g. So that is f prime of x plus g prime of x.